Okay, yeah. So we're now recording, and it seems to be fine, but we can wait a little bit before your talk. Okay, so should we begin? Is that okay? Okay, great. So it's a pleasure to have Atsushi Ito with us from Nagoya. So the topic of his talk is linear systems on abelian varieties via M regularity of Q twisted sheaves.
So thank you for introduction. And first, I'd like to thank the organizers for giving me the chance to talk this seminar. So today I want to talk about linear systems on abelian varieties. So let's start from introduction. First, we recall some known results on linear systems on abelian varieties. So let X be an abelian variety and A be an ample line bundle on X. And then it is known that the A2 tensor A is base point free. And furthermore, if we tensor A 3 times, then it is very ample. And furthermore, it is known that it is projectively normal. And if K is greater than or equal to 4, then the line bundle AK is very ample. And if we embed X into the projective space by AK, then the homogeneous ideal of X is generated by quadrics. And these results are generalized, has a generalization as follows. So let P be a non-negative integer. Then if K is greater than or equal to P plus 2, then kth power of A is Pz ample, which is proved by Bauer and Schoenberg. And soon later we will define jet ampleness, but here we note that 0 jet ample is equivalent to base point freeness, and 1 jet ampleness is equivalent to the very ampleness. And hence, if P is equal to 0, the Bauer and Schoenberg result said that AK is a 0 jet ample, that is base point free, if K is greater than or equal to 2. So this recovers the statement A. And if P is equal to 1, then their result said that AK is 1 jet ample, that is very ample, if K is greater than or equal to 3. So this recovers the first statement of B. And ABC has another generalization, and it is a Lazarsfeld conjecture, which states that if K is greater than or equal to P plus 3, then AK satisfies property NP. And soon later, I will explain the definition of property NP, but N0 is projective equivalent to the projective normality, and N1 is equivalent to the projectively normal, and the homogeneous ideal is generated by quadrics. So this Lazarsfeld conjecture, and this conjecture is already proved by Pareski, and gives recovers P and C. For example, if P is equal to 0, then Lazarsfeld's conjecture said that AK satisfies property N0, that is projectively normal if K is greater than or equal to 3. So this recovers the latter statement of B. And if P is equal to 1, then this conjecture states that AK satisfies property N1 for if K is greater than or equal to 4. And since N1 contains this condition that homogeneous ideal is generated by quadrics, so P equal 1 case recovers the statement C. And so in this statement, so we know that some base point freeness or very ampleness or projective normalness or some blah, blah, blah for A2 or A3 or some multiple of A. So maybe it is natural to ask, what can we say about the linear system A itself, not the multiple of A? And in this talk, we don't need the definition of jet ampleness or projectivity property NP, but we briefly explain the define. We briefly explain the definition of these properties. So let X be a projective variety and L be an ample line bundle. And then L is called P jet ample if this natural restriction map is surjective for any x1 to xp plus 1. And here, so x1 to xp plus 1 are not necessarily distinct p plus 1 points in X. And this ix1 to ix2 blah, blah, blah is the maximal ideal corresponding to the points. And so this is the ideal of X. And if this natural map is surjective, then it's called P jet ample. And hence, if P is 0, this is nothing but globally base point freeness. And if P is equal to 1, then this condition is equivalent to very ampleness. And this is the definition of P jet ample. And for property NP, so let's assume that L is very ample, and if we embed X by the complete linear system L. And let S be the polynomial ring corresponding to this projective space. And then the section ring of L has a natural structure as graded S module. So we can take minimal free resolution as of this section ring as graded S module. And then we can define the property NP as follows. So NP holds for L if and only if first condition is E0 is S. So E0 is here. So the first condition is E0 is S, the polynomial ring. And for EI, so I is from 1 to P, EI is the direct sum of S minus I minus 1. So this is so S minus I minus 1 is the free S module. The grading is shifted by I plus 1. And this is the definition of NP. So for example, for if P is 0, then there is no condition about EI, but we have only this condition. So N0 is if and only if E0 is S, but E0 is S if and only if the natural morphism from S to this section ring is surjective, since this is the minimal free resolution. So N0 is nothing but the projective normality. And for N1, so by this condition, we know that N1 contains N0. And the next condition is E1. So E1 is the direct sum of S minus 2. And since the E1, E0 is S, the kernel of the map from E0 to the section ring is nothing but the homogeneous ideal of X. So the condition that E1 is the direct sum of S minus 2, if and only if the homogeneous ideal is generated by quadrics. So we have this equivalence. And as I said, so we don't need this definition in the rest of this talk, but important point is that jet ampleness or property NP consists an increasing sequence of positivity property of L. So roughly, so these are positivity property about L, and if P becomes larger, then the condition becomes stronger. And so property NP on curves is well understood. For example, so let X be a smooth projective curve of genus G, and L be an ample line bundle. Then Green proves that the degree of L is greater than or equal to 2G plus 1 plus P, then NP holds for L. And we know that classically it is well known that if the degree of L is greater than 2G, then L is base point free. And if the degree is greater than or equal to 2G plus 1, then L is very ample. So hence, this Green theorem can be a natural generalization of these classical results for higher P. And for higher dimensional case, so there is a question about NP. And in some papers, so it is written that this question is due to Mukai. And let X be a smooth projective variety and L be an ample line bundle on X. Then this question asks, NP holds for Kx all time tensor kth power of L if K is greater than or equal to dimension X plus P plus 2. Of course, so this question is quite similar to the famous Fujita's base point freeness or variampleness conjecture. And if X is a curve, so the dimension of X is 1, then so this condition about K is greater than or equal to P plus 2. K is greater than or equal to P plus 3. And since P plus 3 is here in Green theorem, so this question has an affirmative answer for curve by Green theorem. However, so for higher dimensional case, then this question seems to be not known yet, even for the next simplest case. That is, so even for the case of dimension X is 2 and P is 0 case, this question is still open, as far as I know. On the other hand, so when X is an abelian variety, the Rutherford conjecture, which is already proved by Pareski, said that the kth power of L satisfies NP if K is greater than or equal to P plus C. And this P plus C is, of course, smaller than or equal to this lower bound. So since dimension X is greater than 1, so when X is an abelian variety, this question has an affirmative answer. So in this sense, so for multiple of L, so we have some satisfying answer about NP on abelian variety. So today we want to consider when NP or jet ampleness holds for an ample line bundle on abelian varieties. And we mainly want to consider a general line bundle L, which is not necessarily some multiple of another line bundle, not written as AK. So this is today's main topic. So this is the introduction. And now, so I will explain the notion GV and regular and IT0 on abelian varieties and its application to linear systems on abelian varieties. And throughout this talk, so let X be an abelian variety of an algebraically closed field K in any characteristic. And we set X hat the dual abelian variety of X. And P alpha is an algebraically trivial line bundle on X corresponding to a point alpha in the dual abelian variety. And let F be a coherent sheaf on X, and we set Pi is equal to the set of alpha such that Hi of F tensor P alpha is does not vanish. And then F is called GV or M regular or IT0 if and only if the codimension of Vi is greater than or equal to I or greater than I, or Vi is empty for any positive I. This is the definition of these three notions. And for example, so let L be a line bundle on X, and then the cohomology of a line bundle on abelian varieties are well understood. So we can see that L is GV if and only if L is NEF, and L is M regular if and only if L is IT0, if and only if L is ample. And furthermore, so let I0 is the maximal ideal sheaf corresponding to the origin, then I0 tensor L is IT0 if and only if L is ample and base point free. So in these cases, so these three notions correspond to some familiar notion about line bundle. And recall the Lazarsfeld conjecture, which states that if k is greater than or equal to p plus 3, then ak satisfies NP. And Paraski and Popper improved this bound, so the bound is means as p plus 3, improve this bound when A has no fixed divisor. That is, so when A has no fixed divisor, then the kth power of A satisfies NP if k is greater than or equal to p plus 2. And we also need to assume p is greater than 1 here. But in any way, so in Paraski's Lazarsfeld conjecture, so the bound is p plus 3. But if we assume that A has no fixed divisor, then p plus 2 is enough. This is Paraski and Popper's result. And these results by Paraski and Paraski-Popper are proved by the notions GV, M regular, or IT0. And recently, so Zhang and Paraski extend these notions to Q-twisted setting. And here, so a Q-twisted coherent sheaf FXL is the equivalence class of a pair F and XL of coherent sheaf F and ample line bundle L and rational number X by the equivalence like this. And roughly, so FXL is equal to F tensor X power of L. So X is a rational number, but the intuitively, so FXL is so can be considered as this tensor product. And Zhang and Paraski define the GV or M regular or IT0 for Q-twisted coherent sheaf FXL as follows. So FXL satisfies this notion if and only if the pullback of F by mu B, where mu B is multiplication by B isogeny on the abelian variety X, and the pullback of F by mu B tensor LAB is GV or M regular or IT0, then we say that the Q-twisted coherent sheaf Fx is GV or M regular or IT0. And this definition does not depend on the choice of A and B, which satisfies X equal A over B. And we note that this sheaf, the pullback of F by mu B, tensor LAB, can be considered as the pullback of the Q-twisted sheaf by mu B. This is because the pullback of L by mu B is algebraically equivalent to B squared times L. And hence, the pullback of XL by mu B is algebraically equivalent, can be considered as algebraically equivalent to ABL. So since I said that FXL can be considered as F tensor LX, so we can consider that this sheaf is a pullback of FXL by mu B. So Zhang and Paresky's definition said that Q-twisted coherent sheaf FX satisfies this notion if and only if the pullback satisfies this notion. And another remark is that if Fxl is GV, then Fx prime L is IT0 for any x prime which is larger than x. So this means that if x is sufficiently small or sufficiently negative, then Fxl is not GV. And if x is sufficiently large, then Fxl is IT0. And by using these notions, Jan, Paresky, and Couch prove the following theorem. Let I0 be the ideal sheaf of the origin of X. And then I0 XL is IT0 for any rational number X which is greater than 1. And I0L is IT0 if and only if L is base point free. This is the first statement. And the second one states that if I0 twisted by 1 over P plus 2L is IT0, then L satisfies NP and L is P plus 1 jet ample. So this is their theorem. And this theorem gives a very quick and characteristic free proof of Rutherford conjecture as follows. So if P is greater than or equal to P plus 3, then this Q-twisted sheaf, which is equal to this Q-twisted sheaf, is IT0 because K over P plus 2 is greater than 1. And in this case, this sheaf is IT0 because by the first statement of their theorem. Since X is greater than 1, then this sheaf is this Q-twisted sheaf is IT0. So this Q-twisted sheaf is IT0 if K is greater than or equal to P plus 3. And hence, AK satisfies NP by the second statement. So second statement says that if this Q-twisted sheaf is IT0, then AK satisfies NP. So their theorem recovers Rutherford conjecture in any characteristic. And precisely speaking, so the Paresky's proof of Rutherford conjecture need some assumption about the characteristic of the field K. Something like a characteristic does not divide P plus 1 or P plus 2 or something. However, so their theorem by Jan and Paresky and Cauchy, their theorem does not assume and has no assumption about characteristic of the field. So this gives a characteristic free proof of Rutherford conjecture. And because that Paresky and Popper improves the bound in Rutherford conjecture when A has no divisor, we state that if A has no fixed divisor, then AK satisfies NP if P is greater than or equal to P plus 2. And as they improve the bound in Rutherford conjecture, we can improve the second statement of giant Paresky and Cauchy theorem as follows. So theorem A states that if this Q-twisted sheaf, and this is equal to the Q-twisted sheaf in the above theorem. So theorem A states that this Q-twisted sheaf is M regular, then L is P plus 1 jet ample. And furthermore, if P is greater than or equal to 1, as in the theorem of Paresky and Popper, then L satisfies NP. And recall that by definition, M regular is weaker than IT0. So this theorem A improves the second statement of the above theorem, at least when P is greater than or equal to 1. And furthermore, so since the Q-twisted sheaf I0L is irregular if and only if L has no fixed divisor, theorem A gives a quick and characteristic free proof of Paresky-Popper's theorem by a similar argument to this proof. So theorem A also generalizes Paresky and Popper's theorem. And I will explain the idea of the proof of theorem A briefly. Paresky and Popper reduce the property NP and jet ampleness to the global generation of a suitable sheaf on X and apply the following criterion. This criterion is by Paresky and Popper and called M-regularity criterion by them. So let A be an ample line bundle and F be a coherent sheaf on non-abelian variety X. And then if F tensor A minus 1 is M-regular, then F is globally generated. And if F tensor A minus 2 is M-regular, then this natural multiplication map of global sections is surjective for any K which is greater than or equal to 2. And Paresky-Popper using this criterion and show the suitable coherent sheaf and show a global generation of suitable coherent sheaf, and which implies NP or jet ampleness. This is the idea of their proof. And similarly, so theorem A can be proved by using the following criterion. This criterion is in some sense, this defines the original M-regularity criterion. So let L be an ample line bundle, and we take a positive rational number X such that I0XL is GV. And let F be a coherent sheaf on X. And the first statement is that if F minus XL is M regular, then F is globally generated. And the second statement says that if X is less than 1 and F twisted minus X over 1 minus XL is M regular, then this multiplication map is surjective. And because that I0L is always GV for any ample line bundle L. Hence, at least we can take x equal to 1 here. So then the original first statement here can be recovered by the first statement if we take x equals 1. And similarly, so the second statement of the original criterion can be recovered from the second one in this QTST setting. So as I said, so we can apply this irregularity criterion in QTST setting to some suitable sheaf, and then we can show the global generation of the sheaf and which this implies NP or J tamponness, and we can prove theorem A. This is the rough idea of the proof. So we move to the next section. And in the previous section, I explained this result by Jan and Pareski and Karchi and myself. And by these results, it is important to know when I0XL is GVM regular or IT0. In fact, so if we want to apply this result, then we need to know that this QT sheaf is IT0 or M regular, or we need to know I0XL is GV. So to apply this result, we need to know the M regularity or GV M regular or IT0 of this QT sheaf. So in the rest of talk, we consider this problem in some cases and apply this result. And from here, we assume the characteristic is equal to 0. And let L be an ample line bundle on aberrant G for X. Then we can define a sequence of integers d1 to dg such that di divide di plus 1, which is called the type of L. And I don't define the definition, I don't define the type here, but for example, so L is a principal polarization if and only if the type is 1, 1, 1, 1, 1. And D1, so D1 is here. So D1 is 1 if and only if L is primitive. That is, L is not a multiple of another line bundle A. And there is a theorem by Duval, Hurek, and Spandau. So let XL be a general polarized aberrant G-fold of type 1, 1, 1, 1D. And here, so if we fix the type, then we have some suitable modular space. And the general means that XL corresponds to a general point in the modular space. And then L is base point free if and only if D is greater than or equal to G plus 1. And L is birational onto the image if and only if D is greater than or equal to G plus 2. And L is very ample if and only if D is greater than G's power of 2. This is by their theorem. And for projective normality, so there is a following conjecture by Fuentes Garcia. So let XL be a general polarized aberrant G-fold of type 1, 1, 1, 1D as in the above theorem. And then this conjecture said that L is projectively normal if and only if D is greater than or equal to G plus 1th power of 2 minus 1. And we know that this direction and projective normality implies a bound of D easily follows from this condition. So if L is projectively normal, then there is a natural surjective map from this symmetric product to E0 of L2. So, and from this condition, we have easily obtained this lower bound of D. So the essential part is the converse direction. And the converse direction is proved for at most, so if G is at most 4. For when G is equal to 2, and this follows from Lazar's-Feld over Ayer's result. And if G is equal to 3 or 4, then Fuentes-Garcia proves this converse direction by using Ayer's result and some suitable computation of matrix, the computation of rank of suitable matrices by using computer. In any way, so this conjecture is already proved for when G is at most 4. And for general XL of type 1111D, as in the Duval-Hurek and Smander theorem and Garcia's conjecture, so we can show the following theorem about GV or IT0 of this Q-twisted sheaf. So Theorem B says that if let X and L be a general polarized abelian variety of type 1111D, and let M be a non-negative integer, then the Q-twisted sheaf I0 twisted by 1 over ML is GV if and only if D is greater than or equal to G's power of M. And furthermore, this Q-twisted sheaf is IT0 if and only if D is greater than or equal to this number. And we also know that Zhejiang gives some condition of D1 to DG so that the Q-twisted sheaf I0 XL is IT0 for general XL of type 1 D1 to DG. So in Theorem B, we only consider type 1111D, but he consider any type. On the other hand, so Zhejiang's bound for the type 1111D is larger than the bound in Theorem B. So Theorem B does not follow from his more general result. In any way, so as a corollary of Theorem B, we obtain the following statement. So let XL be a general of type 1111D. Then L satisfies NP if D is greater than or equal to this number. And this corollary easily follows from Theorem B and Jan and Paresky and Cartier's theorem, because if this Q-twisted sheaf is IT0, then this implies NP for L. And hence, if we apply Theorem B to the case when M is P plus 2, then we obtain this corollary. And in particular, if we consider P is equal to 0, then we see that Fuentes-Garcia's conjecture, which states that L is projectively normal if and only if D is greater than or equal to this number. And so this conjecture is true as a particular case. And I also explained the sketch of proof of Theorem B. And first, we show that GV or IT0 of the Q-twisted sheaf I0 XL is an open condition when XL varies in a family. And here, so we fix X, we fix the rational number X, and we vary the polarized abelian variety. Then this condition of GV or IT0 is an open condition in the family. And hence, to prove Theorem B, it suffices to find one example of type 1111D such that this Q-twisted sheaf is GV or IT0 because it is an open condition. And in fact, so we can construct such example as a suitable polarization on products of some elliptic curves. This is the rough sketch of the proof. And in Theorem B, we consider the bound of D for GV or IT0. And then, how about irregularity? And I think so one natural expectation is the following, so which said that I0 twisted by 1 over ml is M regular if and only if D is greater than G's power of M. And in fact, so this direction can be checked. This part is not so difficult. And so for the converse direction, there is some evidence. So if the converse direction is true, then we can recover the following results by Duval, Hurek, and Spandau, as I explained before, and another result by Grass and Popescu. So this suffices to say that if D is greater than 1, then L has no fixed divisor. And if D is greater than G's power of 2, then L is very ample. And last one said that in dimension 2 case, L satisfies N1 if D is greater than 9, which is equal to the square of C. And if the converse direction is 2, then these three results are recovered by Theorem A. So this is some evidence for this expectation. And at this moment, I don't know how to check this expectation. But if this expectation is true, then the corollary of Theorem B is said that NP holds for L if D is greater than or equal to this number. This is the corollary of Theorem B. And this bound is improved as follows. So the bound here is weakened as here, if the converse direction is true. So I think it is interesting to consider this expectation, the converse direction is true or not. And in the last section, so I will explain about some abelian three-fourths case. And as in the previous section, we assume the characteristic is equal to 0. And based on Huang and To and Lazarsfeld, Paresky, and Popper, and the following result is known for abelian surfaces. And the theorem by Kronia and Rosvanu, and which is slightly improved by myself, said that let X be an abelian surface and L be an ample line bundle such that the self-intersection number of L is greater than or equal to 4 times square of P plus 2. Then the following two conditions are equivalent. The first one is NP holds for L. And the second condition is that the degree of C, which is elliptic curve in X, with respect to the ample line bundle L, is greater than P plus 2. So this theorem states that under this numerical condition about self-intersection number of L, and the property NP can be completely determined by the degree of elliptic curves with respect to the line bundle L. And we know that, so about this condition, at least when P is equal to 0, then the condition is sharp, since there is an example of X and L, such that the self-intersection number is equal to 16, so this is the equality case, and 2 hold, but 1 does not hold for P equals 0. So at least P is equal to 0, so this condition is sharp. And next, so in this theorem, so we have 2 conditions about intersection number, this one and this one. And if we divide L by P plus 2 like this, and these 2 conditions can be written as the self-intersection number of 1 over P plus 2L is greater than 4. And the intersection number of 1 over P plus 2L times C is an elliptic curve in X, is greater than 1. So we can rewritten like this. And here we recall Fujita's best point freeness conjecture and its stronger version by Corral. So let Y be a smooth projective n-fold and L be an ample line bundle on Y. And we fix a point Y in X. And we assume that the self-intersection number of L is greater than or equal to nth power of n. And we also assume that the degree of any subvariety Z, which contains the point Y, is greater than or equal to the dimension Z power of n, like this. And then this conjecture said that in this case, Ky tensor L is best point free at Y. And this is a strong version of Fujita's best point freeness conjecture by Corral. And based on the above results by Clonia, Rosbanner, and myself, and Fujita's best point freeness conjecture, we asked the following question, question NP. So let X and L be a polarized RVN G4. And let P be a non-negative integer, and we set P is equal to 1 over P plus 2L, Q-line bundle. And we assume the intersection number of, so this intersection number, in other words, so the degree of Z with respect to B is bounded from below by this number for any abelian subvariety Z. And here Z can be X itself. And if we assume this condition, this question asks, N0 holds for L or not. This is the question NP. And from this question, and his own result, Couch asks another question, so question IT0. And this question asks that let X and L be a polarized abelian G-fold. And we set Px is equal to XL for rational number X. And assume that the self-intersection number of Bx and Z is greater than or equal to this number. This bound is same as bound in question and P for any abelian subvariety Z. And here Z can be also X itself. And this question asks, under this assumption, I0XL satisfy I0XL is IT0 or not. And so this assumption about intersection number is quite similar to that in Fujita's best point freeness conjecture. But there is some differences. So compared to Fujita's conjecture, in these questions, we assume we assume lower bounds only for abelian subvarieties. So of course, so Fujita's conjecture consider any projective variety. So the subvariety in the Fujita's conjecture, so we consider all subvariety Z, which contain 0. But in these questions, so we only consider the lower bound of abelian subvarieties. So this is the first differences. And the next difference is that the lower bound in these questions is smaller than that in Fujita's conjecture. So in these two questions, the lower bound is this number. And this is smaller than the bound. This is bound in Fujita's conjecture. So in this sense, so the bound is, the assumption is weak in these questions. And we also note that if the affirmative answer to the question IT0 implies that of question NP. So this is because by Jan and Palevsky and Cauchy's theorem, so I0 twisted by 1 over P plus 2L is IT0 implies NP for L. Hence, if question IT0 has an affirmative answer, then if we apply the case, if we consider the case when x equal 1 over P plus 2, then we will also obtain an affirmative answer of question NP. And so question and so affirmative answer of question NP follows from question IT0. So we mainly consider question IT0. And then for these questions, we have the following result. So when G is equal to 1, in other words, so X is an elliptic curve case. So in this case, so this is easily checked using, for example, Riemann log or something like that. And in dimension 2 case, so this question has an affirmative answer by the result of Colonia Roosevelt and myself. And in dimension 3, this question has a partial affirmative answer by Roosevelt. Roosevelt is considered question NP in 3-dimensional case, but his proof also gave a partial affirmative answer for question IT0. And partial means that he assumed the bound is his assumption about the bound is like this. And original assumption is this part is cube of 3, so this bound is 27, and this is 4, and this is 1. So the bound here and here is slightly bigger than the original question, but in any way, under this lower bound, question IT0 has an affirmative answer in 3-dimensional case. And in higher dimensional case, so the Lazarsfeld, Palevsky, and Popper's result, and by the result by Nakamae about stationary constants, we obtain a partial result in any dimension. And partial means that instead of this bound, we assume some stronger lower bound like this. And more recently, so Jijan proves gives a more stronger result that his result improved this bound. So this is a dimension z power of g times dimension z, but he replaced this g by 2. So he greatly improves this bound, and this is close to the original bound compared to this bound. Anyway, so these results are known for about question IT0. And the last result in this talk is Theorem C, which gives an affirmative answer to the question IT0 in three-dimensional case. So in other words, so let X and L be a polarized abelian threefold, and Bx is equal to XL for positive rational number X. And we assume the self-intersection number of Bx is larger than 27, and the intersection number of Bx and abelian surface is greater than 4, and Bx intersection number of Bx and C is greater than 1 for any elliptic curve C. And under this numerical assumption, then I0 XL is IT0, which is nothing about the affirmative answer of question IT0, and hence this gives an affirmative answer of question NP in three-dimensional case. And as a corollary of the theorem C, so let L be an ample line bundle on an abelian threefold, such that H0 of L is greater than or equal to 5. And this condition is equivalent to the self-intersection number of L is greater than 27. And under this condition, so L is base point free if and only if the intersection number of L and S is greater than 6 or equal to 6 for any abelian surface S in X, and the intersection number of L and C is greater than or equal to 2 for any elliptic curve C. So this corollary gives some simple equivalent condition for base point freeness on abelian threefold under this condition. And so I think so this equivalence is very simple, but as far as I checked, so this equivalence is not known yet, and this is new as far as I checked. And I also remarked that so this corollary, the statement of this corollary, so that is so that this equivalence does not hold if H0L is equal to 4, since there exists an ample line bundle on a simple abelian threefold X, such that H0L is equal to 4 and L is not base point free. So for this L, so L is not base point free, so this condition does not satisfy. But since X is simple, so this right-hand side condition is empty condition, so this is trivially satisfied. So this, in this sense, so this condition is sharp. So I stop here. So thank you for your attention.
Great, thank you very much for the talk. Thank you. Okay, so any questions? Do we have any questions? It's pretty late here in Australia and Japan, so maybe local people are too tired. So hopefully people from Europe, they're more relaxed this morning. So if you have any questions, please do ask. Okay, so if not, I want to thank the speaker again for the great talk. Thank you very much. Okay, so let me just first stop recording to be safe.